Okay, so let's start with this Composite Part 2 webinar. So today we are dealing with kinetic simulations on thermosetting during a thermosetting curing process. So today we will continue with our Composite webinar series. Part 1 took place in the end of November last year, and Part 2 is today dealing with kinetic simulations, here especially with the use of Kinetics NEO and how Kinetics NEO can improve your process. I will show you how easy it is to use. I will tell you a user story where we improved the process with Kinetics NEO, and you will get a more or less deeper look into the use of Kinetics NEO so that you will get a picture in your mind how easy it is to use to work with Kinetics NEO. Because Kinetics NEO was designed that even unexperienced users are able to simulate the process and to optimize the process without being an expert before. So first, a few words to my person. My name is Alexander Kalupka. I studied physics at the University of Augsburg in Germany. Then after my study, I went over to a Fraunhofer Institute for Chemical Technology. Here I worked for the branch Functional Lightweight Design, where we dealt with the entire manufacturing route of composite materials. So from raw material characterization in the lab, we are process environment, post-process quality assurance, online monitoring, quality assurance during the process, life cycle assessment, and recycling as well. Since summer 2016, I'm working for NETZSCH Analyzing and Testing. Here, I'm working as an R&D engineer in the field of dielectric analysis. And I'm acting in the business field polymer. Please be aware of the upcoming webinars of the Composite series. So Part 1 took place in November. Part 3 will be at the end of February, where we deal with dielectric analysis, where I will give you a deeper insight into how to use dielectric analysis for real-time in-process material characterization. And Part 4 is at the end of March, where we deal with dynamic mechanical analysis, because glass transition determination using the DMA technique is one of the standard processes in quality assurance. Please be also aware of the free of charge seminar that is upcoming. So we have 3 locations where this seminar takes place. We have 2 locations in Australia and 1 location in New Zealand at the University of Auckland. It's free of charge, so if you live there, if you're interested in, please register and have fun there. Your input is very, very important. So let's pick up some information we got from the webinar Part 1 in November, so that everybody of you who hasn't participated the first webinar will have an idea what we did, what were the results, and what we could find out in comparison of kinetics, quality assurance after process, and in-process material characterization. So in Part 1 of the Composites webinar series, we told you a story of a material manufacturing where the customer didn't know how to process the material. So we did the material characterization using differential scanning calorimetry, and we used Kinetics NEO to set up the process, so to find out the right parameters for a short cycle time and a high mechanical performance of the material. Then we manufactured a composite test plate where we implemented dielectric in-mold sensors. These dielectric in-mold sensors were able to detect the temperature of the material at the sensor location. Then we could detect the flow front. So when did the flow front arrive at the sensor position? And we measured the cure behavior of this resin during processing. Afterwards, we prepared samples out of this test plate, and we did a post-process quality assurance using differential scanning calorimetry to determine the residual cure, and we use dynamic mechanical analysis to determine the glass transition as a quality criteria of the mechanical performance of the material. If you didn't join us in November, in the presentation I uploaded for you in the upload window, there you can find a PDF of this presentation I show you today. You can upload it and you can click on the GoToWebinar Series 1 part link. So there you will directly link to the video and you can replay and watch the Composite Part 1 webinar. What we found out during the last webinar was that even doing kinetic studies on this pure resin, doing an in-mode material characterization using dielectric analysis, and doing post-process dynamic mechanical quality assurance, we found out that the resin wasn't fully cured after the end of the process. So we could see that Kinetics told us before that using this cycle that was used to use for the customer resulted in a still ongoing curing at the end of the process. Dielectric analysis as in-process quality assurance confirmed these results, and also dynamic mechanical analysis, so the glass transition temperature location, shifted from the first to the second heating. So we could see that all of the measurements we did resulted in the same results. Today, we are dealing with phase 1 of this webinar series. So today, we are dealing with generating measurement data for kinetics modeling. So I will show you how to use DSC data to do kinetic modeling and to predict process conditions. And I will give you a deeper insight into kinetics modeling using Kinetics NEO. So doing this, I will tell you a story of a customer. So around 1 year ago, a customer called me and he said, the datasheet of our material says that for infusion processes like we do, we have to heat up the material from room temperature to 80 degrees C. Then at 80 degrees C, the flow behavior of the resin is the best. So we have the lowest viscosity at these 80 degrees C. And we need around 30 minutes for infiltration. Subsequently, we heat up to 160 degrees C with a heating rate of 2 Kelvin per minute. And we have to hold the 160 degrees C for 30 minutes for a fully cure. That's what the datasheet told them. And he told me as well, these results are very, very good. So we reach a degree of cure of more than 95% and a glass transition temperature that is above 160 degrees C. But they have other requirements. So he told me that mechanical tests on samples showed that a degree of cure of more than 90% and the glass transition temperature above 150 degrees C is sufficient for their application. But their big handle is to save the cycle time during production. So he told me that they have to save at least 10% in manufacturing time for the curing process. And his question was, can you help me? Can you show me what we should do during manufacturing? And I said, yes, we will do that. So I said, send me 200 milligrams of your sample, and we will do that for you. So we did the measurements with the samples, and we used the cycle of the datasheet to see what Kinetic told us about the cycle time of the datasheet. And we could confirm the data of the datasheet. So the datasheet says, after the cycle, we have a glass transition above 160 degrees C. You can see this at the red line. And the orange line gives you the conversion. The conversion is very close to 100%, so to 1. And the customer told me the datasheet says we will result in a degree of cure of more than 95%. So it's all right. But before I show you the benefit for the customer and the results we could generate for him, let's do some kinetic basic stuff. So now we will talk about what is kinetics, how to use kinetics, and then I will show you again the query of the customer and how we could solve it. So first, what is kinetics? The definition of kinetics is, on the one hand, the study of chemical processes and chemical reactions to understand the influences that affect the reaction mechanisms. So influences on the reaction mechanisms, they can depend on the resin hardener mixture, they can depend on the temperature, on the time. So we have to understand what is going on inside a material. And the second part of the kinetics definition is that we have to fit our measurement data with mathematical models. And then we will be able to describe and predict a chemical reaction for each temperature cycle the customer wants to use. So the most important study in kinetics history was done by Svante Arrhenius. Svante Arrhenius studied the temperature and ion concentration dependency of the reaction rate. You can see the Arrhenius equation down there. This is the basis of the temperature dependency of our kinetic software. So let's have a deeper look to this equation. That's the only equation I will show you today, so don't be afraid of that. First, we have a conversion rate. So alpha is the conversion, or often named as the degree of cure. The conversion rate is dependent on the Arrhenius equation, so the temperature dependency of the molecular movement, and a mathematical model to fit the measurement data. And we have different parameters in there, but don't worry about them. We don't have to deal with that. So I will show you the use of Kinetics NEO and the benefit, and will not go too deep into the details. So if you're interested in, please contact us. We can tell you about, but I don't want to make you be afraid during this webinar today. So let's assume we have a single step reaction. So we have a component A, so an educt A, and this becomes, during the chemical reaction, the product B. Then we can see as orange line, at the beginning, we have 100% of product A, of educt A. This educt will decrease during the chemical reaction, and the product B will increase to 100%. And the Arrhenius equation is used to describe this behavior. So the concentration of educt A is decreasing, and with the same ratio, the concentration of product B is increasing. That's what Kinetics NEO is doing in behind, calculating the fit for your measurement data. So now I will tell you about Kinetics NEO, because we developed a very easy to use software for newbies and expert. I told you before, you don't have to be an expert to use Kinetics NEO. Let's have a look into a step-by-step instruction to model this thermosetting cure of the customer material. So what we need for kinetic simulation is we need measurement data. Then we have to model them. After we modeled it, we can do predictions and we can optimize the process for the customer. First, to the measurement data. We need the measurement data first. We got the measurement data using differential scanning calorimetry. For the measurements of the customer, we used our DSC 214 polymer. There are several test standards for differential scanning calorimetry and also standards for the method for the DSC itself. These are the measurement data of the customer's material. So we used 8 different heating rates, and we measured the curing behavior of the customer's material during dynamic heating ramps with this heating rates you can find here from 0.2 Kelvin per minute to around 5 Kelvin per minute. And now Kinetics NEO comes into play when we model these data. For modeling these data, we have two options. The first option is for the unexperienced users. So the first option is really a one-click model-free Kinetics NEO solution. What does model-free mean? Model-free means that the measurement data are fitted with any mathematical model, but you won't get a good understanding of the chemical processes behind. So this is just a mathematical fit of your measurement data like polynomial or exponential without any kinetic model in behind. So this is really the application without queries. And you have to be careful because this model-free kinetics cannot be used for very complex materials and very complex chemical reactions. But let's have a look at that. The material of the customer is quite simple. It's a one-step curing reaction. And the only thing you have to do in kinetics is to upload your data into the kinetic software. And then you can see on the left side, you just have to click to numerical optimization. And then you will get the mathematical fit of your measurement data. With one more click, you can have a look to the conversion. So also often called as degree of cure. And now you would be ready to do predictions on your material. But let's come later to the predictions. Let's have a look first to the more academically way. So the model-based simulation, the second choice you can do. So let's do it more academically. The model-based solution gives you a better understanding of the reaction processes. With this model-based solution, you can fit even very, very complex chemical reactions. But you have to be a little bit more experienced in using kinetics. So we could see that this material shows a single-step reaction. So remember, we have the balanced equations. Component A decreases and component B, the product increases during the cure. If you want to do model-based kinetic analysis, then you first have to analyze your measurement data. Therefore, for differential scanning calorimetry measurements, the Friedman plot is often used. The Friedman plot is a plot of the reaction rate depending on 1000 by the temperature. And this plot is read from right to the left. So on the right, there's the beginning of the reaction. The lines you can see in there are isoconversional lines. This means following one of these lines, every measurement data determined with a different heating rate show the same degree of cure or conversion when crossing this line. And these lines are very important to estimate what reaction mechanism is behind this curing process here. So let's have a look to the right end, so the beginning of the reaction. There we can see that our reaction itself has a higher slope than the isoconversional lines. And this indicates that this reaction is accelerated. So this reaction is an autocatalytic reaction. And by having this knowledge, we can go to the model-based kinetics you can see on the left side, and we can use the autocatalytic mathematical model that is implemented into the kinetics. So you just have to choose, hey, I want to plot my reaction mechanism based on an autocatalytic reaction. Then you can see we have a quite good fit of our measurement data. And a few clicks further, we will get the fit with this model for the conversion. And what you could see now is that our model overestimates the reaction rate from around 60% of conversion on. So this model is not sufficient. So what did we forget to consider? We forgot that in a curing reaction, from a specific degree of cure, we have diffusion control reactions. So what does this mean? In the liquid condition of the resin, the molecular movement is very, very high. So the molecules can move really undisturbed. But from a specific point, it is often the point of gelation. This mobility is hindered, so that leads to a reduction of the reaction rate. Let's have a look to the data again. We overestimated this measurement data from 60% of cure on. So the reaction rate lowered, but we didn't consider. That's what we can see here. But we can take this into account. What we need for this is the evolution of the glass transition temperature of this material in terms of the conversion or the degree of cure. This looks like this behavior. This is the glass transition temperature evolution for the conversion between 0 and 100%. And if we take this into account, we can model the cure behavior at the end of cure, so from 60% to 100%. But to know the glass transition evolution is much more important than just for this kinetics evolution here for the diffusion control processes. Glass transition temperature defines or is one of the key parameters that pretend the mechanical performance of your component part. Not just the layup, also the location of the glass transition temperature that is directly linked to the degree of cure of your resin. So let's have a look to the measurement data again. Taking into account the glass transition evolution, our signal or the fit of the signal doesn't look very different to the one we could see before. But if we have a look to the conversion, then we can see now we have a very good fit to our conversion. And now the model-based kinetic fit is very, very good. And we are ready to predict the customer's issues. So have a look to the prediction. What about the solution of the customer's problem? You remember the customer called me. He told me about the datasheet temperature cycle, and he told me about his requirements. He has to save 10% in cycle time. And the requirements to the material is that we reach a degree of cure of more than 90% and a glass transition that is above 150 degrees C. And we should help him. So we simulated his datasheet cycle and we could confirm his data. Fine. But now we optimized his cycle. So now we have a cycle time of 111 minutes. We optimized his cycle from the step of the 2 Kelvin per minute heating from 80 degrees to 160 that was set by the datasheet. We decreased the temperature, so we got from 80 degrees to 150 degrees C with 2 Kelvin per minute, and then we stopped at 150 degrees C for 10 minutes. And here you can see the evolution of the glass transition and the conversion, so the degree of cure. And the black lines, the black dotted lines, show you from left to the orange curve the requirement for the customer. So he needs more than 90% degree of cure. And from the right axis to the red curve, a glass transition of more than 150 degrees C. And we reached it. But we did this with a time saving of 22.5%. So we saved more time than the customer needs. And we surpassed the glass transition and the degree of cure of the customer's requirements. And that's the big impact, how you can optimize your process by using kinetic modeling and the very easy to use Kinetics NEO software. But we could show the customer more information. We showed him, what if you don't have an infusion process? How would the curing of your material look like for different isothermal temperatures? Here we modeled the conversion, so the degree of cure, in a temperature range of 60 to 160 degrees C with a temperature step of 20 degrees. And we could show him at 140 degrees C, you will reach your 90% degree of cure in less than 50 minutes if you would be able to cure the material at an isothermal temperature in the mold. And Kinetics NEO can do even more. Kinetics NEO can calculate time temperature transition diagrams for you. What are time temperature transition diagrams? Time temperature transition diagrams are like a landscape of your material. This landscape gives you the chance to have a look at it and to determine the values you want to without doing further kinetics evaluation. So you can have a look to this landscape and you can have a look, what temperature do I need for what time to reach my goal? So let's have a look at that. Time temperature transition diagrams give you information about the conversion of your material. What you can see here is temperature versus time as axis and isoconversional lines. These isoconversional lines give you the behavior. How long do I have to process my material at which temperature to reach a specific degree of cure? So, for example, have a look to the green curve on the upper right. We process this material at 160 degrees C and we move down and we could see, okay, we need 50 minutes to reach a degree of cure of 98% at 160 degrees C. And we can follow it, for example, at 120 degrees C. Let's process the material at 120 degrees C inside a mold, and let's follow the evaluation of the degree of cure. So you can see after around 2.5 minutes, we reach a degree of cure of 2%, but after 1,000 minutes, we reach a degree of cure of 90%. That's the customer requirement. So it's the pink line on the right side and the pink dot. So at 120 degrees, it's nearly impossible for the customer to process this material because it takes 1,000 minutes of processing and curing. But we can show more. We can create this black line. How do we do that? We can process this material at 120 degrees C. And we can put in the glass transition evolution at 120 degrees C. And what you could see is that the isothermal temperature of the mold at 120 degrees C crosses the glass transition evolution at a specific point. This is the point where we can see the black curve crosses these 2 points as well. This is the glass transition equals the process temperature line. So with this black line, you will get the information. For example, you have the requirement, I want to have 160 degrees C glass transition temperature. And I want to process my material at 160 degrees C. So then you have to look where is the crossover of the temperature 160 degrees C and the black line. And this is around 30 minutes. And we can do even more. So the fully timed temperature transition diagram looks like that. Here you can see the glass transition evolution for different temperatures from 20 degrees C to, you cannot see the legend, to 160 degrees C in steps of 3 degrees C. And you can see the isoconversional lines from 2% to 98%, like we could see before. And with this material landscape, you can set up your isothermal processes, because then you can follow the time temperature transitions of your material during isothermal cure. And that's a very important landscape for composite manufacturing, because usually you're doing the curing process in an isothermal tempered mold. For example, 120 degrees up to 180 degrees C in aviation, or in automotive at the moment up to 250 or 290 degrees C. And then you can have a look at this material landscape and you can determine your process time and your process temperature to reach a specific degree of cure and glass transition. So this was the short introduction from my side into Kinetics NEO. Now I'm open to your questions. I can see there were some questions during this webinar. I will have a look at that. Please give me some more questions. We have a lot of time to talk about that. And if you're interested in, you can contact me directly, or you can contact us here at NETZSCH Analyzing and Testing, and you will find your way to get the right person in our company. That gives you more information about Kinetics NEO. That gives you more information about how to process my material, how I can use different measurement techniques like differential scanning calorimetry, dilatometry, arc calorimetry, or dielectric analysis to model my cure parameters and my cure behavior during the thermosetting cure. So now I'm open to your questions. I will have a look to the questions that reached me during this webinar. There was a question of Dami Kim. My question is how to calculate the activation energy if the nuclei of samples are exchanging during heat treatment. So you could see Kinetics NEO takes into account the temperature behavior of your material. If the nuclei are changing due to thermal treatment, you have the accessories of Friedman plot Osawa-Flynn wall that take into account the change of your activation energy during the process. So during different temperatures and time. So if your nuclei are changing, the activation energy will change. And this toolings like Friedman Osawa-Flynn wall or numerical optimization can show you the evolution of the activation energy and the pre-exponential factor, so the likelihood factor for molecular collision during your whole process. So you can have a look at that using Kinetics NEO. You can model that and you can see that. And you can take this into account during modeling. So you can split your kinetic models into 2, 3, 4 different steps. The next question in case of the aging, I'm interested in how it is possible to see the material changes. We have a DSC polymer machine. I think the question is splitted. No, it's the whole question. Okay, it's aging. You can model aging with Kinetics NEO as well. So if you do long-term differential scanning calorimetry measurements, you can follow aging, but you can follow aging as well. If you, for example, imagine you have a material and you store this material for more than 1 month, for example. Then you can measure your material at specific time points. So after receiving it from the material supplier, after 2 weeks, after 4 weeks, after 6 weeks, after 8 weeks. And then you will have the changes of your material. So it's the aging factor, because thermosets are reactive materials. So they live. They are not dead till you characterize them. And with this information, you will get the information of the aging of this material. So it's like a pre-curing. And you can take this into account. And then you can model the aging effect on your material and the material quality. Another question regarding measurements of data by differential scanning calorimetry. How do you handle if the 2-component thermoset material separates in the DSC die before curing? So I hope I understand the question right. It's from Brian Lund. So if you're still here, please correct me if I didn't understand it in the right way. You mean you prepare your sample, you have a 2-component resin system, you mix it, you prepare it into a DSC pen, and then you assume that the 2 phases will separate. So 2 components that will separate before starting the DSC measurements. Am I right? Okay. That's quite critical. There are some resin systems with ionic hardeners. I observed this as well sometimes. So due to adhesion forces, it may be possible that the very high conductive ionic hardener moves away and climbs up the walls of the DSC pan. What you will measure during the DSC is, on the one hand, you will see the curing, because the hardener and the 2 components will get more and more liquid during treating of the temperature. And when they get liquid, you will see a mixing again. But it's quite critical, because it's nearly impossible to eliminate all the failures by reason of the separating of the 2 components. So what you can do possibly is to use high temperature DSC. Sorry, not high temperature, high pressure DSC. So with high pressure on the sample, you can a little bit avoid that the components will move. But that's only an assumption. I don't know if this works very well. So that's a very critical point. So if you're not able to generate reproducible measurements during DSC or dilatometry before kinetics modeling, then it's nearly impossible to eliminate all the parasitic effects that will influence your measurement. So the first thing is, if you're able to generate reproducible measurements, then I would say you're on the safe side for kinetic modeling and prediction. But if it's not possible to generate reproducible measurements, then you have to change the method or to find a way to eliminate all the influences. So maybe high pressure DSC would be a good solution for that topic. There's another question. Is it possible to access the software although we don't have any NETZSCH DSC apparatus? Yes, it is. You can have a look on, I will show you. Let's go to the early beginning of this presentation. In the PDF you could download, there is a link to our Kinetics NEO homepage. So you can click here. It's on slice 19. You can click on the Kinetics NEO logo, and then you will be redirected. I think you can see that, to our Kinetics NEO homepage. And on this homepage, you can request a software. So you will get a 30 days full software for your test. And you can also upload measurement files of TA Instruments, of Mettler, of Perkin-Elmer. It doesn't matter. So you don't have to use NETZSCH files for this Kinetics software. Our aim was to give you the possibility also to model your measurement data without having a NETZSCH instrument. And you can click here on request software, then you will send our Kinetics department an email with your contact details, and then you will receive a download link and an activation key for your 30-day trial software. The trial software is a full software, so you can use all the toolings I showed you today. And then you can play around and you can decide if Kinetics NEO is the right software for your application. And on the Kinetics NEO homepage, you have some more things. So you can see what is new. You can see the release history, so what changes from the first release of Kinetics NEO from last summer to now. And you can see the differences between Kinetics NEO and our former version, Thermokinetics 3. You also have a Learn button here. So you can learn how to do kinetic modeling with different measurement techniques and different measurement data. So Kinetics NEO has implemented some test measurement data and test models. So you can play around with that. So they are fully integrated models. You can have a look at how we did the modeling. And here you have a step-by-step how to instruction, how to build up your kinetic model with thermogravimetric analyzing data, dilatometry, differential scanning calorimetry, arc calorimetry, and dielectric analysis will follow as well very soon. And we are continuously working on expanding the possibilities of working with Kinetics NEO. So from time to time, more and more instruments and instrument data will be implemented into the Kinetics NEO software. Okay, another question. Our press process is established at 160 degrees C, curing for 15 minutes. We should decrease the cycle for 10 minutes, but would it be useful to know what is the effect to the pressed part in chemical way 2? How can I analyze it? Please correct me if I don't understand the question in the right way. It's from Henrietta Oswald. So your question is, you have a process you're doing at the moment at 160 degrees C for 15 minutes. You want to decrease the cycle time to 10 minutes or by 10 minutes. Doesn't matter. And you want to know the effect on the pressed part in a chemical way. That's exactly what we do here with Kinetics. So you want to analyze that. Okay, 10 minutes instead of 15. So you want to decrease the cycle time by 33%, so by 5 minutes. What we do here with Kinetics NEO is exactly your question. We analyze the chemical reaction of your material. So when you do kinetics studies, you have to do 2 or more measurements at different heating rates or different isothermal curings you have to use in Kinetics NEO. So you need at least 2 measurements with different heating rates or different isothermal temperatures. That's the requirement for Kinetics NEO to work with your measurement data. And then you can simulate your process you're actually doing at 160 degrees C for 15 minutes. And with this model, you can also see the influence, what happens if you decrease the cycle time to 10 minutes. What will be the degree of cure at the end compared to the 15 minutes curing cycle? Then you can also see, for example, what is the effect on the curing if I go up to 170 degrees C or 165 degrees C and cure for 10 minutes? Do I reach the same degree of cure when doing the process at 160 degrees C for 15 minutes? So that's exactly what kinetics is doing. But you need at least 2 measurements from your lab. So for example, 2 differential scanning calorimetry measurements at 160 degrees C and at 140 degrees C, or 2 measurements, one from room temperature to 200 degrees C with 10 Kelvin per minute, and the second measurement with, for example, 1 Kelvin per minute from room temperature to 200 degrees C. Then you can get the full information of your curing, of your material. Then you can model it with Kinetics NEO and you can do the predictions for your process. Okay, I'm done with, you're welcome. I'm done with all the questions here. Do you have more questions? We have around 8 more minutes to work on your questions. Maybe you can tell me if you were working on components or curing parts in the past where you had big trouble. Maybe you are able to tell me the story so we can talk about that with all the participants at the moment. Because I think it would be very interesting to have user stories of what we did in the past, what went wrong, what we improved. Can we do that, for example, with kinetic simulation? Another question. Is there many people asking about glass kinetics? So you mean the evolution of the glass transition temperature or the when to reach the glassy condition? So from cooling down from a high temperature to a lower temperature. Because for thermosetting materials, okay, for example, I want to know about nucleation rate or grow rate of glass. Yes, we have these questions. We have these questions also for semi-crystalline thermoplastic materials. And in literature, for this example, for thermoplastic materials, you can find that the Aframi exponent is, for example, one magnitude that is often used for characterizing the nucleation rate. And this is something you can do with Kinetics NEO and with kinetic studies. So there you can follow, for example, you have a polymer in the melted state, so a thermoplastic material, and from the molten phase, you cool down the material and you can follow the nucleation rate. And then you can use the Aframi model and you can evaluate the Aframi exponent. And this gives you the information about the nucleation growth. And it's also possible, there are some literature sources that give you also the chance, by having this kinetic model, to estimate the nuclei size, so the diameter of the nucleus. So I have calculated the following question from Damike. I have calculated Aframi exponent and activation energy, but it showed large difference depending on the heating rate. I am working with benzo arsine resin, and the problem is its high cure temperature. Is there anybody help me with some accelerator additives? 2 questions from 2 different people. Sorry for that. Okay, first, Damike. I have calculated Aframi exponent activation energy, but it showed large difference depending on the heating rate. Yes, it does. You can see a large difference depending on the heating rate, but you will also be able to fix the Aframi exponent. So, for example, if you imagine you have a nuclei growth from a thermoplastic material, we did it with PPS, and we calculated the Aframi exponent for different heating rates. So what we did was we went from the molten state and we had to process it. So we had to process composite parts, and we had different isothermal mold temperatures. So from the molten state, the PPS composite part got to see the temperature of the mold at different isothermal temperatures. So for example, 150, 160, 180, 190 degrees C. And with this mold temperatures, the cooling rate changed as well. But we could find out that there is an asymptotic law that it doesn't make sense to go to a temperature of the mold of 80 or 100 degrees C. So we could find out with PPS that a specific temperature is the limit. So it doesn't make sense to go to a lower temperature. But this is exactly what you can find out. And the Aframi exponent, you can fix it. You can fix it and you can have a look at how the activation energy and the pre-exponential factor are changing. So this is another method to fix the Aframi exponent. So if you assume that the nuclei growth is not influenced by the temperature change, but it's often influenced. So the Aframi exponent will change. But if you fix it, if you assume that it's not changing, that the nuclei growth and the nuclei size would be the same, then you can fix it and you can see the effect on activation energy and pre-exponential factor. And that can give you information about how to process your material and how the temperature affects your nuclei growth and nuclei size. Okay, another question. I'm working with a resin and the problem is its high cure temperature. Is there anybody help me with some accelerator additives? Yes. When the problem is the high temperature, it's depending if the resin is temperature activated, so if the curing is temperature activated or temperature and time activated. So if you have some, how's it called? Let me think about, yeah, if you have some inhibitors in your resin and the inhibitors are therefore produced, okay, it's temperature activated. So you have some inhibitors that will degrade, for example, at 180 degrees C or 200 degrees C. Okay, no inhibitors. So what is the temperature the reaction is activated? Because you can change the reaction mechanisms by adding some additives like accelerators, or you can change the resin hardener mixture if you're able to do that. You can add some catalysts that could change the chemical mechanism so that the temperature for the activation is lowered. But this is very much depending on self-curing resin. Okay, so it's a premixed system. So that is very much depending on the mixing of the material supplier. I don't know if you get the information from the supplier, but for this question, you have to contact them and you can ask if it's possible to put in an accelerator, so a catalyst or some other additives that change the chemical reaction a little bit so that the mechanical performance will be more or less the same, but the curing temperature is lowered. But there just the material supplier can help you. So if you know very much about your material, it's possible to simulate the growth and decrease of different components during the cure of your material. But if you don't know this information, then you can just fit it with mathematical models. You think or you assume that they are the right ones for this material and this curing process, but without having any knowledge in the chemical reaction mechanism of this material. So often the material suppliers won't tell you. Then it's quite critical to get more information and all the information you need for your process. Then you can just model it with kinetics and predict what is the material doing at different temperatures. Okay, one last question from Dami Kim. To conclude this, you are saying that I should fix the Aframi exponent to calculate activation energy, nucleation rate, and so on. How could I select certain Aframi exponent? I'm thinking that I may choose a Fermi exponent by observation of microstructure, which provides the information of dimension of evolution. Is this right? Yes, the Fermi exponent depends on the nucleation growth rate and the nucleation size. So it's depending on what you expect from your material. If you assume that the nucleation size and growth rate is not that much depending on the temperature, then you can fix the Fermi exponent. And then you can see the effect on activation energy and pre-exponential factor. So to your question, how could I select certain Fermi exponent? Do you already use Kinetics software? No. Okay. During kinetics modeling, you can fix parameters. So you can do the first model, you can find a quite good fit, and then you can fix 1 or 2 parameters that will never be chosen by a further adaptation of your model. So you can fix parameters, and then you can find out how activation energy and pre-exponential factor are adapted to reach this very good kinetic fit of your material data, of your measurement data. Okay, so thank you very much for your participation. I really enjoyed it with your questions. You had very, very good questions, very, very informative questions, I think, for all of the people here. And if you're more interested into the Kinetics software, please contact us. I hope you downloaded the PDF file with the presentation in there. And I hope to get more and more information from you and to hear from you if you have further information, if you have further questions and you need further information. So thank you very much. Have a nice day.